All right. Now let's take a look at more of those problems, but this time the z-score will not be given to us. All right, so when we pull the a value out of the table, it'll be in decimal form. And what it's telling us is the relative area. So when you get that decimal, it's telling us the relative area under the curve for some region, like the relative area of this region if we assume the whole is 1. So you'll get things like, 0.463. All right, but that 0.463 can be thought of as the area under the curve, or it could be thought of as the probability of an item lying in that interval, being there. And the probability could be reported as a decimal or as a percent, right? So sometimes you say there's a 46.3% chance, but typically probability and area are normally written as decimals, okay? But it's also telling you the percentage of all the items that would lie in that interval. So these two are normally decimals, and this one is normally written using a percent, okay? But all of them are done the same way. All right, now what's happening here that's different is we don't already know the z-scores. We have raw data. So here we have a fruit packing company. They made peaches. The weights we were told were normally distributed. The mean was 14 ounces, meaning 14 ounces would be right there at a z-score of 0. Standard deviation was 0.6 ounces. So I could do like I did before and add 0.6 and get 14.6, and then add another 0.6 and get 15.2, and add another 0.6 and get 15.8. But the thing is, now that we know how to use the table, what they're asking us for doesn't have to wind up being right at one of those standard deviation lines. So I could do that, and I could go in the other direction. I could subtract 0.6. And if I did that, I could label those. So I have a sense of where we're talking about. So if I want to know, first question is, how many of the peaches could we expect in our sample, could we expect to have weights that are less than 14 ounces? So 14 ounces is the middle, less than that over here. Okay, so I'm going to do this one in green. Wouldn't that be 50% of them? So we would take 50% of the 1,000 peaches, 0.50 times the 1,000 means about 500 peaches would have weights less than 14 ounces. Okay. Now, the next question is, about how many could be expected to have weights between 14.9 and 15.5? So, 14.9, that's going to be about right here, more than somewhere in there, maybe about halfway. And then 15.5 would be somewhere in here, and we're looking for that. So what you need to do is take your raw data value and calculate the z that's associated with it. So I'm going to try to keep myself straight about where I'm at. So the z-score for 14.9 I would find by taking 14.9, subtracting the mean, and dividing by the standard deviation. All right, so that gives me 1.5. All right, then take 15.5 and calculate the z-score that corresponds to that raw data value. So that's 15.5 minus 14 divided by 0.6, and that one equals 2.5. Okay. Now let's go to the A, find the A that's associated with each of those z-scores. So these are z's, right? These are z-scores. So I go to 1.5 and I see that the A that corresponds to that is 0.433. And from the table, the A that corresponds to this z-score is 0.494. All right, but think about what we're trying to do here. We're trying to get this, right? So 49.4% of the data would be from that spot, that high thing, all the way to the middle. And then 43.3% would be from there to the middle. So I want that. So it's a subtraction problem. See how those z-scores are on the same side of the mean? So I would need to subtract them. So I'm going to take the 49.4% and subtract the 43.3%, and that gives me, what is that, 6.1%. So I know 6.1% of the peaches would have weights between 14.9 and 15.5, and my sample consists of 1,000. So when I do 0.061 times 1,000, I actually get around 61 peaches. Okay. So what's happening on these problems is you have that added step of having to find the z-score first. All right, let's try another one. All right, the times taken by workers to assemble a certain kind of cell phone are normally distributed. The mean is 18.5. Okay, so mean would be 18.5. The standard deviation is 3.6. So I could go and I could label these by just adding 3.6 and adding 3.6 and so on. If I added just even 3.6, I'd be at 22.1. Okay. All right, but you don't really need to label that. What you're going to do instead is you're going to create a z-score, find a z-score for these. So I could have gone in and subtracted the 3.6. I could have taken the 18.5 and subtracted the 3.6. I don't have a calculator handy. And that gives me 14.9. So it happens to be right there at the -1. But you're being asked here. Nobody mentioned that you could use the empirical rule. And typically you wouldn't have even labeled these here, okay? I'm just trying to give you a sense of how to think about the problem. So what you would do first is you would take the 14.9, think of that as your x. Get the z-score associated with that 14.9. Okay, so you would take your 14.9, subtract the mean, and divide that by the standard deviation. When we do that, we happen to get -1. Okay. Now, if we go to our table where there's a 1 in the table, the A that's matched up with that is actually 0.341. Okay. So that means the table, you know, always gives you from your z-score to the mean. So that means here would be 34.1%, okay, of the data values. All right, now we want to know, find the probability that one such phone will require less than 14.9 minutes in assembly. Okay. So we actually need this right here, less than that in assembly. So like times that would be from here down. So I'm going to take 50% and subtract the 34.1%. And that would give me, what is that? 15.9%. So over here would be about 15.9%. And it says find the probability. So there'd be a 15.9% chance the probability of requiring less than 14.9 minutes, okay, would be 0.159. Okay. If it said require more than that much time, then you would have added 50% to the 34.1. Right, let's do one more. Okay, here we have the fish problem again. Average length of fish caught is 11.6. Standard deviation of 3.6, meaning each of these would be up 3.6. Each of these would be subtracting 3.6. But we're not told we could use the empirical rule. Find the probability that a fish caught there will be longer than 16 inches. So this is your raw data value. The z-score corresponding to that could be found by taking 16, subtracting 11.6, and then dividing by 3.6. Okay, that turns out to be a z-score of 1.22. So then you go to your table and you get the A corresponding to that, and the A corresponding to that is 0.389. All right, now the 0.389, okay, would be from our z-score of 1.22 to the mean. That 0.389 would be that 38.9% of the fish would have lengths that would fall between the mean and 16 inches. We want the probability the fish is going to turn out to be longer than 16 inches. So we want this part here, okay? So that means we would take 50% and subtract the 38.9%, and that would give us 11.1%. So we would expect 11.1% of the fish to have lengths longer than that. So the probability of having a fish with a length bigger than 16 inches would equal 0.111. All right, now just remember, it might have said, suppose that the lake had, what if we took a sample of fish from the lake, maybe we took, what if we had something like 500 fish in our sample, and we want to know how many of those fish we'd expect to be more than 16 inches, then we would take 11.1% of the 500, and we would work that out. Okay. So that was not the question. That was to be aware that you have the skills to do that. All right, let me get my calculator. 0.111. So if we had a sample of 500 fish, we'd expect around 56 of them. 56 of the fish to have lengths more than 500 fish. All right, and then let me do another what if back on this one. So back here, the question was, find the probability a phone will require less than 14.9 minutes in assembly. What if it had been, let me do it in purple. What if they had wanted the probability that required more than 14.9 minutes? Well, we still have the information we need. It's just more than would have been from there all the way up. So see how on this side would be 50%? 50% would be more than the mean. So if you needed more than 14.9 minutes, you would have taken the 50% plus the 34.1%. You would have gotten 84.1%. So that would be a probability of 0.841. See how it would be 1 minus that? Okay. All right, so you got to be ready. You got to be able to draw the picture so that you know what you're being asked. So you keep straight, which way you're supposed to be handling things, whether you're going to need to add or subtract